Hi, everyone, and thank you for joining our podcast. My name is Ivailo, and we're also joined by Nelson. Nelson, good morning.
Good morning, everyone. Hi, I'm Nelson, and welcome again.
Yes, and today we want to share with you one of our daily stand ups. And we did our sprint planning on Friday, so we just want to show the results of this sprint planning. I think it's going to be very interesting. So, Nelson, let me open the ticket about the next 2 weeks, the next sprint, and we can discuss what exactly we want to achieve for the next 2 weeks. So, if you don't mind, please go ahead and just give us a brief overview about the tickets we plan to achieve and resolve.
Sure, Ivailo. Well, as you can see, probably we have a plan for the next 2 weeks. Plan is basically have 4 items. These 4 items is the development of and understanding of the junction conditions to a deeper level, which is something that we need to understand quite correctly uh, to get to the warp drives and how to work with them. So the first step is finish to reproduce a thesis. We found a thesis, interesting thesis is uh, quite large, which we are using as a base. We are using this as a steps that we need to understand of how junctions conditions are going to work and everything else. In this thesis, basically what these guys did is that they propose a couple of metrics, space times inside and outside. That mean exterior and interior metrics, which are specific form, which is both are spherically symmetric, and they work on the first and the second fundamental form. So this we are using, or we use because we already did that to understand how to implement. I mean, how to make the exactly calculations that we need. Usually in the literature, you see a lot of how is the theory works and from the differential geometry point of view. But in this case, we wanted to make to feel some sense of how you get to hands dirty with the calculations, which is very nice. But this also have other elements in the thesis. We have the first and the second fundamental form, which and the second fundamental form what you have is the construction of the extrinsic curvature. And you using this extrinsic curvature, you also define other things, which is where in this the stage we are now. Where by this you define uh, what you can call some sort of Einstein equation that you might say on the surface. This hypersurface, which both the interior and exterior metrics met, and this is called the Langsos equations. So, and this has needs to have some very specific properties, and we're working on those properties right now. I mean, in fact, Gabriel is doing that. He found like there are some he's obtaining different results, so we're looking into that. And also there is another approach which is also in the thesis, that where you project the energy momentum tensor that you have, a more or less general energy momentum tensor on the surface, and you use this projection to make some continuity of this, and then also you can find very interesting and junction conditions. And this is an approach that is very well known. Both approaches are very well known, but this one is in fact being used in interesting lectures given in a school of gravitation at the end of the 90s. Yeah, and it was by this guy, Luis Herrera Cometa. He's a very well-known guy in the general relativity community. You can check the guy. And then this he made this for an solution which is internal solution, spherical, and external spherical solution, which has also the possibility it allows the exterior metric for dissipation. So we're doing now, and Gabriel is working very hard with this, and also implementing a mathematical notebook. We are trying to make automatization of everything as much as we can. Uh, he's trying to reproduce this by using both methods. The one with the first and the second fundamental form, which means to look at the Langsus equations on the surface also, and also projecting the energy momentum tensor on these ones. So we plan to have this well understood and done, yes, in a couple of weeks, and then use this for starting working with the 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 warp drives. This basically comprises the item one and item two of the sprint planning.
All right, and what about the rest?
Yeah, let me go to the rest. The rest one is something that I've been working by myself, which is reviewing Natarius papers. We decided that Natarius approach was more general than Cuvier's. It's been modified by many authors to solve some problems, but we're trying to understand the original one, completely original one. So, and these jobs, what I'm doing is, yes, looking into all the propositions and theorems he's is putting in the article, proving those, and also implementing in mathematical notebooks. For this, I started from the very beginning, and from the beginning, just it's quite simple. What you do is you want to understand uh, how an observer, which is basically the whole problem in general relativity. You have a space-time, you have a configuration space-time, and then you need to see the phenomenological part comes when you define an observer. And from this work, yeah, I mean, for the Natarius approach, you have what we call Eulerian observers, and these observers are the ones that are in free fall. Let's call what you call free fall observers, which are defined by geodesics equation. And these geodesics equations basically it's like telling you how is the Newton's law in a curved space modified with something or by something that you name Christopher symbols of the second type, or the gammas in general relativity, which is these quantities that maybe you can hear or read, has all the derivatives of the metrics, and these are very fundamental, in fact, in general relativity. In fact, they're used in other fields that are related to general relativity to define gauge fields, for example, and so on. But that's another topic. And this, in our case, the point is to calculate these Christopher symbols or connections. They are also called connections. And you calculate this, and with this, you can derive the geodesic equations. This is not the approach that Natarius did. Natarius worked using a different but very interesting approach. He uses the action in terms of when you can review in classical mechanics, or well, in quantum field theory, of course, but you can start with classical mechanics book. You see you have the action, which is defined through the Lagrangian, and then this approach is very nice because Natarius did was basically define a Lagrangian and then obtaining Euler-Lagrange equations, which are the equations of motion of this the Lagrangian. Very nice approach. You obtain a couple of equations which defines how is the behavior of the each of the coordinates in terms of some other parameter, which in our case is going to be the proper time. So the point with Notarius is that if you do this and you obtain a couple of equations, you obtain two because basically you have two degrees of freedom. Well, four in fact, but you have time and x and their derivatives with respect to the parameters. But when you solve Euler equations, Euler-Lagrange equations, these two are a coupled system. You have two equations that are very well coupled. And if you want to, from there, which is the usual approach in these cases, if you from there want to obtain, for example, Christopher symbols, the connections, you have to decouple these equations and then identify what is it that is in the equation that looks like the Christopher symbols. This is not the approach that I wanted to do. This I wanted to make the more traditional approach, which is quite straightforward. Is looking at the definition of the geodesic equations and then calculating. And to compare, I need to decouple Natarius equations and just compare and see that they both both agree. And that's what I've been doing. Of course, I wanted to do this using mathematical implementation. I did it by hand first, and from the geodesic equations point of view, which is okay. And then I started to implement in a notebook. The implementation with the notebook took a bit longer than I was expecting. It was a bit more complicated to get everything right. The proper definitions, everything. I mean, you have to define everything correctly. The right index, how you have the contravariant and the covariant index have to be correctly put. So I put together a very large notebook, and I finished very late last night. But at the end, I found the solutions. Was then at the end, I just took Natarius equations and I decoupled, but just by calculating in a paper, and everything went very well. So now the next step is to go to the next proposition, start, or I think it's the next proposition. And of course, when we have all this done, hopefully this very week, yeah, we will go on the new results for us. I mean, which is implementing all these tools that we are learning with the warp drives and see what problems arise, what the difficulties arise, and also what the results are coming for us.
So we're going to start with the fun part. Nelson, thank you very much for putting the time and resolving this notebook in the evening. Actually, you spent a lot of time in the night. Do you mind to share with us a little bit more what was the issue? What took you so long? I mean,
Okay, sure. You want something more technical? For one hand, let me see. At first, I was using a notebook, a previous notebook that Gabriel and I developed, and it wasn't working. It wasn't working in the sense that I was decoupling the equations from Natario, and I was obtaining something, and I was obtaining something completely different with the notebook. So to check that, what I did was, okay, let's go to the basics. Let's try to do it with Schwarzschild. And Schwarzschild solutions are very well known, and the geodesics are very well known. So I plugged Schwarzschild metric. You have to make a few changes in the notebook, and I didn't obtain the Schwarzschild geodesics. So there's something was going on. At the end, apparently, what I did was I just start from scratch. I forgot about that notebook and start working again. My belief, and I'm going to discuss this today with Gabriel and with the notebook, is there was something in the definition that we're using. I think we are defining correctly the the uh, the connections uh, in the theory, but with a difference in the index. And I think when I'm trying to implement that in the previous notebook, that this difference in the position of the index changed everything. But I wasn't able to find where exactly was the problem. I tried a lot of permutations and nothing was working. And in fact, then I used this to you use these quantities to define the Riemann tensor, and I use it to make the define the Riemann tensor and obtain then Einstein's equations. I mean, you take the trace and you take Ricci tensor and so on, and I found something was ultimately was wrong. So well, I redefine everything. I mean, I define everything again in the notebook, and it looks fine. Also, on the other hand, I noticed that was missing something that was very nice. This is more anecdotic than science, but this if you work too late at night, and this is was 1 in the morning, and you don't have the same cognitive capacity. So I was making a silly mistake, making a derivative. I was forgetting an implicit derivative, which is going to give me a couple of additional terms which are there, and I was not getting these terms, and I was going crazy. And then I realized, of course, you have an implicit derivatives. Please go do this, and I did it, and everything was fine, and I went to bed very happy.
So thank you very much, Nelson. And just to give some clarification, when we do this research and these equations, we always use mathematical notebook because we want to automate everything. And uh, the other benefit of the mathematical notebook is that we can change something in the beginning, and the mathematics notebook, they're going to do all the calculations for us. Because of that, we do the majority of the work by hand, but at the same time, we automate it with mathematical notebook, right?
Yeah, that's correct. These calculations are, uh, I mean, for very symmetrical systems, the calculations by hand are more or less straightforward, but they still are very long. But in fact, once you start losing these symmetries, this is going go completely crazy. I mean, I can give you a brief example. If you and obtaining these equations for Natarius works. Natarius is doing this in a specific direction. He's using x direction, just as the motion of the bubble isn't going to be in the x direction. But if you try to make it more general, like saying you have x and y direction also, this is just everything explodes. You have equations that are very large, very hard to just analyze by hand. So you really we need this type of uh, automatic calculations. But of course, you have to check and check and check again with known results and with other symmetries, just to see to have the confidence that it's going to work well. But that's completely true. I mean, at some point you need to stop and then calculate something else by hand, small calculations. But the hard part, I mean, what you call the force brute calculations, need to be done with some mathematical notebook.
Nelson, thank you very much for explaining all of that. Is there anything else you want to add in addition to everything you said about the planning we did for the next 2 weeks? Anything else we want to share with the listeners?
Well, yes. If you're listening and you have any ideas, please let us know right here, right here in the comments, or go to the Patreon and subscribe and make the comments there, or ask any questions. I will be happy to answer any questions that you have, if I can. As I mean, I'm learning a lot, and we can learn a lot together, which is going to be very fun.
Excellent. Thank you very much, Nelson. And thanks everyone for listening to this podcast. If you like it, please subscribe and like the video. And if you feel like supporting us, you can do this on Patreon. And we're going to share the link below. And with that, again, thank you very much for joining. And I wish to all of you to have a very nice and successful week.